greetings of the day. This is the second session on stability analysis. In the first session on stability analysis, we discussed different types of the stability, concepts of stability, and analyzing stability or identifying the stability of the system using Routh-Hurwitz criteria. So in this first special cases of the Routh-Hurwitz criteria. The case 1, there are different cases. So the case 1 is zero element in first column of any row. So that is, for example, S4 row is something 1, 20, 50, S3 is 500, and while calculating S square, 5 into 20, 100 minus 1 into 100, 100. So 100 minus 100 becomes 0. Whereas this element 5 into 50 minus 1 into 0 divided by 5 means 50. So first element of any row is 0. So if we continue the table, all the element becomes 0 or infinity. So in this case, checking the sign of the first column is difficult. So how to resolve this? There are two methods. So method 1 is epsilon method. So in such a case that any first column of any row is 0, resolving this difficulty by epsilon method. So in this method, replace this 0 by a small positive constant epsilon and proceed to complete the table. And stability is decided by applying limit as epsilon tends to 0. So if I apply to this particular case, so 1, 20, 50, S cube is 500, S square, instead of 0 I have substituted a small value epsilon, positive value. Now I will complete the table. So epsilon into 100 minus 250 divided by epsilon. So S to the power 1 table completed by 100 epsilon minus 250 by epsilon. This is 0 because no element in this. And S0 column is this one. So we have completed the table. Now the question is, what is the sign? Because we are not interested in the value, sign is important because the stability depends on the sign of the first column. If all elements are having same sign, then the system is stable. If there is sign changes, system is unstable. So I need to find what is the sign in this. So for this, we have to apply the limit. So for third row, limit epsilon tends to 0. To this side, if I substitute apply a limit as epsilon tends to 0, it becomes a 0. 0 means a positive value. So fourth row, limit as epsilon tends to 0, 100 epsilon minus 250 by epsilon. So if I apply epsilon here, so what I will get? As epsilon equal to 0 here, so 0 minus 250 by 0. So minus infinity. So instead of the value, if I check on sign, this is the negative. So that means in the first column there is a sign change. So system is unstable. So this is the positive sign. S1 row is negative sign. So if we see positive, negative and positive. So two sign changes in the table. So two poles are on right half of the S plane. Positive to negative, negative to positive. So two sign changes, so two poles are on the right half of the S plane. Second method is reverse coefficient method. So if first element of any row is 0, method 2 is the reverse coefficient method. So in this method, substitute S is equal to 1 by X and develop a new Routh table and examine stability. So substitute S is equal to 1 by X and develop a new Routh array table and examine the stability. For example, I will consider this as a characteristic equation of the system. So for this particular characteristic equation, table becomes like this. Same as the previous one, 1, 20, 50, 500, S square is 0 in this. So according to reverse coefficient method, I will substitute S is equal to 1 by X in this characteristic equation. So 1 by X to the power 4, 1 by X cube, 1 by X square, 1 by X into plus 50. So it is not that 1 by X plus 50 equal to 0. So if I rearrange this, taking X to the power 4 common, so 50X square plus 100X cube plus 20X square plus 5X cube plus 1 equal to 0. So now write the table for this. So by writing the table, S to the power 4, 50, 21, 50, 21, 100, 5. So if I complete this, 100 into 20, 2000 minus 250, 1750 divided by 100 is 17.5. 100 into 1 minus 0 divided by 100, so it is 1. So 17.5 into 5 minus 100 divided by 17.5 is minus 0.7143 and S0 is 1. So what happens? The system is unstable because there is a sign change in the first column, and two poles are on the right half of the plane because there is a two sign changes, positive to negative, negative to positive. Now we will consider the case 2. The case 2 is all the elements of one row are 0. It is something like this. S to the power 5 coefficient is 2, 5 and 10. S to the power 4 is 4, 10 and 20. So in this case 4 into 5, 20 minus 2 into 10, 20. So 0. 4 into 10, 40 minus 2 into 20, 40, 0. So this situation occurs only when preceding two rows are proportional. So this is multiple of 2 of this row. So these two, if I divide each and element, I will get a same ratio. So these two rows are proportional. So all element of a row becomes 0 only when preceding two rows are proportional to each other. So in such a case, how to find the stability? So first step, obtain auxiliary polynomial equation. Means it is a polynomial where the coefficient are the elements of the row just above the row of all zeros. So here S cube row is a 0. So I need to obtain the equation from S4 row. So this is 4s to the power 4 plus 10s square plus 20 equal to 0. This is the auxiliary polynomial equation. So after obtaining an auxiliary polynomial equation, differentiate auxiliary polynomial equation with respect to S. So if I differentiate this auxiliary polynomial, I will get 16s cube plus 20s equal to 0. So after differentiating, replace the rows of zeros by the coefficient of differential polynomial. So this row is to be replaced by this polynomial coefficient and complete the root table. So in this case, this 0th row I am replacing by 16 and 20. And if I complete the table, 16 into 10, 160 minus 80 divided by 16 is 5. 16 into 20 minus 4 into 0, so 20. 5 into 20, 100 minus 320 divided by 5 is 44, 20. So in this, after completing the table, I need to check the stability. So stability, there are different steps. So any sign changes in the first column indicate the system is stable. After replacing this row with all zeros by auxiliary polynomial coefficients, still there is a sign change in the first column, then system is unstable. There may be chance there is no sign changes in the first column of the system. First column. Then the stability of the system depends on dominant pole obtained by auxiliary equation. So we need to find the solution of the auxiliary equation. And if the roots of the auxiliary equations are positive real values, then it is unstable. And suppose if the roots of the auxiliary equation are negative real values, then stable. If the roots of auxiliary equation are non-repeated imaginary values, then marginally stable with frequency of oscillation is imaginary value. So for example, J2 plus or minus J2 if we get as a root, then it is marginally stable with frequency of oscillation 2. Now if the roots of the auxiliary equation are repeated imaginary values, then unstable. Now for the given example what we have considered previously, this given system is unstable because there is a sign change in the first column. So let us consider one example. A unity feedback system is defined by characteristic equation s to the power 6 plus 2s to the power 5 plus 8s to the power 4 plus 12s cube plus 20s square plus 16s plus 16 equal to 0. Test its stability and find frequency of oscillation. So first we will form Routh-Hurwitz table. So s to the power 6, highest order is s to the power 6. So row s to the power 6 is coefficient of s to the power 6 1, then difference by 2, that is s to the power 4 coefficient 8, then difference by 2 s square coefficient 20 and constant coefficient 16. Now next s to the power 5 coefficient is 2, s cube coefficient is 12, s coefficient is 16. So first two rows always obtained from the given characteristic equation. Now we will obtain s to the power 4. S to the power 4 is 2 into 8 divided by 16 minus 1 into 2, 12. 4 divided by 2, 2. 2 into 20, 40 minus 16, 24 divided by 2, 12. 2 into 16 minus 0 divided by 2, 16. So here if you see these two rows are proportional. Obviously we need to get next one 0. So 2 into 12 minus 2 into 12, 0. 2 into 16 minus 2 into 16, 0. So I will get 0, 0. So all the elements of this row are 0. So in this case what we need to do? Obtain auxiliary equation. Since all the rows of s cube is 0, consider the auxiliary equation from s to the power 4. That is 2s to the power 4 plus 12s square plus 16s is equal to 0. So differentiating this auxiliary equation, I will get 8s cube plus 24s equal to 0. So first two step we finished. Now I need to replace this coefficient in this place. So after replacing s cube 0, 0, 0 by 8, 24, 0, so I will complete the table. So what will happen? 8 into 12, 96 minus 48 divided by 8, so it is 6. 8 into 16 minus 0 divided by 8, 16. Next 6 into 24 minus this one, 2.6670, 16. So in this case all the elements of first row are of same sign. No sign changes in a first column. So in this case what we need to do? we have to find the roots of this auxiliary equation, then we have to decide the stability. Since all the elements of first row are of same sign, stability depends on dominant poles. So auxiliary equation is 2s to the power 4 plus 12s square plus 16 equal to 0. So if I find the roots of this, I will get the roots are as j1.414 minus j1.414 plus j2 minus j2. So here roots are imaginary as well as non-repeated. All are different. Plus or minus j1.414 plus or minus j2. So since roots of the auxiliary equations are non-repeated imaginary, system is marginally stable with the frequency of oscillation 1.414 and 2 radians. So there are 2 frequency of oscillation. So this is about the stability of the system. So in this session we have studied special cases of analyzing stability analysis using Routh-Hurwitz criteria. Thank you.